Good evening. I'm going to launch straight in with where we are and come back to why and what in a moment. The laser pointer is a bit distracting when you don't actually want it. In the middle of that map, there's an arrow which points to Aberfeldy. You can see it's pretty close to the middle of Scotland. Up here, we've got Fort William, somewhere around there, landed somewhere. Fort William is here. Dundee out on the Tay estuary is there. Aberfeldy's on the Tay, which flows from Aberfeldy down and out past Dundee. And as everyone who grows up in the area knows, the Silvery Tay flows up to Perth, but twice a day. So your tidal limit is about there. We're going the other direction. This is very rough, but the catchment at Aberfeldy takes in this rather hilly area that goes well over to the west coast of Scotland and picks up quite a lot of rain and quite a lot of snow. So when you're designing a bridge to cross the Tay, it's a 50-metre-ish width of river, but you have to allow for quite big floods. Basically, it's an enormous mountain burn. You switch to a satellite map and start zooming in. This is Aberfeldy here and Loch Tay just upriver. And we've now got the village, the golf club, General Wade's Bridge from 1733, which had been long-term study of Bill and Fraser at the point that the story we're telling today starts. And round here is the Linksleader Bridge. That's Wade's Bridge with a good bit of modern safe access arrangement. The golf club wanted to expand over the river from 9 holes to 18. And part of the planning was that they couldn't have golfers crossing this bridge, which is only just wide enough for a car. So they needed a bridge. History. We're here in the history group. This is 1992, just a few years ago. I was there. How can it be history? I was a little bit nonplussed when it was suggested that we should do a talk about this. But it was the first major all-composite footbridge in the world, first bridge built with pultruded glass reinforced plastic. There had been a couple of previous ones with hand laminated, like people were building canoes. And it went straight into the Guinness Book of Records for the longest span plastic footbridge, and it's still there at 63 meters, or as the drawing said, 63.001 meters. Everything in pultruded GRP, except the cables, which were Kevlar, synthetic fiber, and a few aluminium components to connect the cables to the bridge, a few steel tubes to support the towers and to attach the cables to, and some reinforced concrete, very limited reinforced concrete in the foundations. How did it come about? Dundee Civil Engineering had built a few small bridges, and Bill, obviously with Fraser, was working on the Wade Bridge over a long period and knew the golf club. A member of the golf club asked, "Can you help us? We need a bridge. We've got no money." He had seen a call from Maunsell Structural Plastics for a site for experimental GRP footbridge and approached Peterhead. They met up in London and Bill pitched Aberfeldy, and the pitch went something like, obviously, the special property of this material is its weight. So there's an opportunity to assemble and erect a very large bridge with minimal plant. We don't need a crane. We don't need any plant heavier than an excavator or a telehandler, and that only occasionally. So how about you, Maunsell, coordinate contributions in kind from the supply chain? We bring site experience, Bill's and Fraser's site experience, and also a labour force of final year students. And together we do something really special, not just a bridge, but a landmark. Oh, and by the way, the golf club doesn't actually have any money. So there was a big list of people involved, and many of these put in substantial amounts of in-kind support. So when it came to the GRP product, the whole supply chain contributed in kind. The labour force was students from Dundee University, some from Darmstadt, some from Glasgow, some members of the golf club, and the odd school kid Bill would pick me up from school on a Friday night, take me up there for the weekend, drop me off, often slightly late on a Monday morning. Fortunately, that was before the days when schools had worked out they could fine parents for children missing school. So the Dundee students did some design as a final year project, but it wasn't their design that went into use, but just as another demonstration of the fact that this really is history. This was the state of computer graphics at the time. Pultrusion. There you go. That's been around a while. There's for those that aren't familiar, basically you've got a roll of woven glass fiber. It gets pulled through a liquid resin tank and then taken through a heat treatment, and you end up with sections like that. They can be quite complex in shape, but these are the basic parts that went into this bridge. The panels are about 600 by 80, and the square connector pieces with 3 notches are 80 by 80, and then there's a toggle that goes in between to hold them together while the adhesive goes off. The overall design in long section looks a bit like that from the side. You can see the side beam, you can see a main cross beam and lots of intermediate cross beams. And looking at a cross section at each of those, you have a thin deck, just 1 panel thick, and cross beams underneath, and a multi-piece sidebar, which will, in practice, look like those. And that's the hanger on the end. And the only last thing I want to say before handing over to Fraser for the stories of the pain of building is that obviously this is extremely light. And so one of the last stages was to cut little slots in the deck and slide in blocks of varieties cement ballast that then got pushed along inside. So the whole thing is then made heavier once it's complete.
It's still much, much livelier than the wobbly bridge in London. Okay, so titles, engineering and ingenuity. We had a number of problems, and these are the list of things that really had to be solved because there wasn't any specific way of doing them. And this one in red, we will meet later on, but it was the most important thing and nobody knew how it was going to be done. So we will move on from these. Okay, stage 1 foundations, very quickly. That was done by a local contractor. And Bill and I set it out when we came back from survey camp in the summer, and the things all got built for us. Delivery of materials. You can see here that, you know, students are I think they're actually carrying 2 planks at a time there. This is them all stacked up, so it's a very easy material to handle. So Hamish has already shown this one, but we have the dog bone in here, which is what joins the things together. There were things like this were glued on these intermediate faces, and the deck was made from one of these, another one of those. Three deck panels and 4 box sections. There was problems, which we'll come to. So when they were started working, they couldn't get the dog bone to slide down through the groove, and they were trying with the end of a file to file the excess material away. When I came along and saw what it was doing, I thought there must be a better way, and I thought, So I got some blocks of timber, trapped the file in between, and they could then easily just ride it along, and suddenly they were able to slide a dog bone from one end to the other, which was fantastic because it was taking forever to do it as it was. So that was the first problem solved. The edge beams. Now, the edge beams had to look like that to start with. So the holes for the main cross beams, and you can see at this point that there's a gap which laps over onto this bit, but when it gets put together, there's going to be a big hole there for the crossbeam to go into. So a jig was made up in this tent where we did all the work, and things were glued together and put on the jig. And this is a jig in action. So you can see the posts here leaving the holes for the small cross beams. And this here is a full railway sleeper that was suspended off the top frame of the tent, and it had enough kinetic energy to break the stiction and keep pushing the things in without smashing it. When we started, people were hitting it with little hammers that just frayed out the ends of the dog bone. Then we tried a bigger hammer, and then we went onto this, and it worked. When we got onto some of the deck building, we used a half sleeper, and this is a piece of Teflon plate on the end to protect the dog bone. So that's the edge beam assembly. The deck beam, there's our tunnel built on a slope leading up to where the tower is going to be. Gave us a bit of protection, a couple of 4x3 timbers for the deck to sit on temporarily while it was all put together. And here's the first panel completed, with a couple of long panels in the middle and the side ones. So the dog bones in this case had to slide quite a long way in to secure the next next plank into position. Yeah, quite light to handle. And you see here there's some holes in the edge. This is where the handrail posts are going to go in the future. So yeah, this is how to split the dog bone with a metal hammer. You can just see it's starting to get a bit furry. This was, yeah, they broke it trying to get the things in. This was before we'd got onto the the sleeper driving. So the deck, all this stuff had to be put together quite accurately. So here they are setting out the arrangements of bits and pieces to get so that we kept these cross ports open and the handrail holes in the right places opposite each other. So that worked really quite well. And when it was proposed by Bovis Lendlease, who were doing the safety thing on it, we were going to have almost 2 meters each side of it. There's so much scaffold, it was taking up half the golf course. But we trimmed it down and made it more cost effective. So that was that one done. Now, one of the main items of the build were the towers. This is the second tower going together. I think this is even the Hamish on the end of it here, isn't it? Yeah, yeah. So this was a piece of plant being used to do things. We didn't have many items where there's plant involved, but you can see here there's holes in these two sections. It's tapered, a long taper at the top, which has to come together. And these pipes, which are all loaded up with teardrop shapes to pick up the stay cables, were already fitted together. It's a steel pipe, but with offcuts of plastic water main pipe clipped onto them or pushed onto them to keep it all located together. So you've got a fair sized bit here, a tiny bit in the middle to just stop the ends of the cables touching each other, and bit in the middle. This is where the legs are getting dropped down onto a cribbage of sleepers at both ends to support them. So we added some instrumentation. One of the postgrads that was working there was doing some of this, and I can tell you when it was getting done, it was a very hot period, and being inside there where there was glass fibre dust was not pleasant, because I was helping put them in. And unfortunately, the adhesion of things to the surface of the towers after pultrusion, most of it fell off before it could do anything. So that's what we were doing there. Now here's Bill stood in between the two sections, adding the cables. These things were pre-set up. You can see here the hole where the cable pin is going to get, or the termination pin is going to go in to hold it. When we get to this one, you see that Bill is not happy. This was the last one, the one that was going out to near the middle of the river, and those cables, because they were much flatter, were heavier to take to give the extra stiffness, and the pins on the ends here were 2 mil bigger. And somewhere down through this lot was one that was wrong. So it involved going back down through, shaking out each one of them, trying to work out which one rattled most, and then opening the whole bloody thing up again, taking out the pipes, and getting the offending piece off, putting this one back on to where it should go, and then putting it all back together. So you'll notice, by the way, that a lot of these photographs are dark. There's a simple reason for that. This is likely to be 9 or 10 o'clock at night, because our shifts starting at sort of 8:30 or so were open-ended. Yeah, it was tough. But we eventually got there, and we've now got the pin in the right place. And he's smiling, which is good. So we then had to glue the things together. And here I am with a 4-meter long spanner with a 13 mil socket in the end of it, going right down through the tower joint. There was a plate on the outside here. Have you got a mouse? No. Yeah. There was an outside and inside there, there's an outside and inside here, and the same on the bottom too. So there's a lot of plates that needed to be fixed. And access to them by this time now, with the pipes in for the cable anchorages, wasn't easy. So there was had to be some cooperation between the people that were working on it to do it. And getting that pipe down the end with a socket and getting it popping up through the right place was, yeah, interesting. And then somebody could put a nut on it. So, yeah, but we did it. One of the things that helped slightly was to super glue the washers and the nuts onto the fiberglass so that they were in place, but it did obstruct the vision slightly. Some of it worked and some of it didn't. And when we were finished, there was the completed splice down through. So it gives you some ideas. I think it's about 4 meters long or so. Then it came time to try and put the tower up. There's some other bits and pieces here, but these bases were cast, and they were wide enough apart for the tower to go straight down into, but they took no account of the fact that the legs were coming down at an angle into the base. So bits had to be cut off. So there's chunks of the box section cut off here, and a fair bit of hammering and whatever to remove some concrete there to get it in place. There was also another thing that had to be done there, which I haven't got a problem thing for, but you see these plates here, which were also inside outside on these 1, 2, 3, 4 faces. We had to thread the pipe through the plate, through the wall of the leg, through the other hole, etc., all the way across, so that these plates could be bonded in place to stiffen up the connection there. It was not easy to do, but it was something we had to do. Then we got on to the point of trying to raise it. This thing could get dropped in, and we could put the big pipe through underneath again, right through the thing to act as a hinge. And we had a turfer pulling on a wire, which is attached to a sling at the top of the tower. And the theory was that we would push this tower up to 30 degrees, and then we'd be able to pull it up. Well, we were supposed to be able to pull it up, but somebody had forgotten that cables sag. So whilst the intended line is the straight line, the actual line comes up at quite a lot shallower to the tower, so there just isn't enough force. After we'd broken about 4 shear pins in the turfer, we decided that it probably ought to have another way of doing it. And then for the next time, we did get some help. So we've got a couple of things, diggers here, and there's a telehandler down the end here that's going to push it up just that bit further than we could get it before. And it worked. So there's another one solved. The next thing was to think about building a launching nose. Bill knew all about launching noses because he'd worked on several big jobs where big beam bridges were built up together and then launched out across, in fact, the Tay on one of them. So, yeah, that was a problem that we needed to solve, but a little bit out of order here, maybe. But at this stage, we still didn't know how we were going to lower the deck down around the cross beams. We used to have lunch and dinner in the clubhouse, courtesy of the golf club. And many serviettes were consumed in trying to get a scheme to actually do this process. Yeah. So onto the cross beams. The cross beams consisted of 4 of the boxes together. They were stood on end, and there was some packing put in to seal the thing off at about this depth. And then the whole thing was grouted at the top with the aluminium section around it, or the aluminium casting, which was going to take the cables. This was because there was going to be some really high loads going through here. Here's the whole set of them ready to go, all marked up for whichever bit they're going to go into. And then these had to get strung out across the river in a bit of a cat's cradle so that we could launch the deck out. So here is the cat's cradle starting to get pulled out. You can see there's a couple of cables here. This end one has got 2 cables going back to the tower base on the other side. Lorna here is holding things back, just waiting for the next one to get pulled out. And Rory looking on, lazy devil that he was. But between each of these cross beams was another cable, and you can see here there's a turnbuckle or a bottle screw, which was used to adjust the length. I adjusted them all to length and got it wrong. all stressed out from both sides once we got the 2 towers up. And then we are ready for the deck launch. So we've come back now. We've got the launching nose to think about. We've got the gap in the edge beam. And we still haven't worked out how to lower the deck around the cross beams. So tomorrow, yes, we had Tomorrow's World come to film. It was a wonderful day. They came on when we were launching the deck. Started off fine and got so far, and they said, "Oh, can you stop a bit, and we'll get something else done." And we ended up at night with gale force winds and a thunderstorm, and finished at gone midnight. Yeah, as you can see. The launching nose was put together, but how do you fix a launching nose to this nice bit of deck that you don't want to do any damage to? I don't know how Bill did it, to be honest. I can't remember it at all, because I was there, but no, it's just more bits of the timber that we were using for the ramps, etc. And it all seemed to work.
If Ed happens to be on the call, he might be able to tell us, because I think he was involved in it.
Okay, right. Yes. So when it got to the other end, it was, that was time to sort of tie it down and hope that it didn't blow away in the wind, because it was an absolutely foul evening. So now we get to the difficult bit, launching the deck and infill of the edge beam. This deck is in its final position here, but when we pulled it out over, of course, it had to go across all of the cross beams. And what do you do with a gap like this? And Bill had a brilliant idea. He got some short bits of the square box section, and he got our technicians in the lab at the university to cut lots and lots and lots of wedges. And the wedges went in there paired up into each box, and the boxes were put in place. There was a bit of dog bone. In fact, you can see a bit of dog bone just there, that white bit, that held that box into place. So that enabled us to get it out, slightly out of order, that of course, but yeah, it was good, but we still didn't know how to drop the deck. And then I think it was far less than a fortnight. It probably was within the last week before we needed to do it that we actually solved it. And it was one of these things that Bill and I could do together quite well, of have silly ideas and misunderstand ideas and discuss things and eventually come out with a solution. And the solution was astoundingly simple. Now, Hamish has billed this as being a bit like the A-team, and that's what it was. We knew all the bits and pieces that we had on site at that time, and we thought, what can we do with these? And that's what happened. So the lowering the deck is the next bit. So here's the deck, and you can see here we've got a turfer. There's a cable running out over the top of this aluminium casting, just enough room for it. The casting butts up against the edge beam. And this is going on further, because what we've got here is the solution to the problem. And I'm sorry, it's the best picture I've got of it. we had blue polyprop rope. We had bits of this 4x3 timber. We had enough turfer wires to join two together and get them to go across the whole span of the bridge on both sides. We were able to lean over the side of the deck and adjust the bottle screws that I got wrong. And we're able to line it up. There was also a plate had to get fixed on here. You can see there's a little white line up there. That's the edge of a fiberglass plate that went in the hole to help distribute the load a bit more. That all got put together, and you can see we've got some nails here to hold the wire in place, and the blue polyprop rope went underneath to stop those timbers spreading as we tightened the turfer up. Tighten the turfer up, it lifts the deck, slacken the cable off, and guess what? It lowers the deck. And it was just so simple in the end. But my God, it was worrying before that we couldn't work out how to do it. But then we had also to clamp the deck down while the glue that was on top of it set against the bridge deck. So the two timbers, or one of the timbers, came out from underneath. The blue polyprop rope was brought up and put between the nails here, and the wedges that came out of the box section got used to pinch together to tighten it up. And then in these cases, this is one of the side spans getting done. This is me adjusting the cable to get the beam in exactly the right place. So that was a weight off our shoulders, because we just didn't know what we were going to do before. Now we had two side spans to build, and that needed doing, and that there were serious problems with that, because by this time we were getting into September. It was raining, and here we've got a bridge that's got a nice camber over the top, and when it rains, the water comes down, and you've got to try and stop it. So we were gluing bits of the dog bone to the deck and trying to run the water into the handrail holes and things like that to give us somewhere dry to work within the tent at the bottom, each side at the same time. And then we had to do things underneath the bridge, because if you think back to the picture of the end of the crossbeam that you saw that Hamish put up the diagram, there was a section to go in underneath the crossbeam. And I don't know if you can see here, but this was faceted. So it was almost straight here, and all the bend happened here where you got these two bits missing at the bottom, and then onto this one, and the same again. And this tapered ended box had to go in underneath and be glued up. And it was easy getting this thing started, tapping the dog bones in to get it in, but trying to close up about a 10mm gap between the box and the deck and or the edge beam was a nightmare, because we were on this rig. That's me moving it, which had absolutely no torsional stability whatsoever. It was fine, it hung underneath, but doing things like this with a 14-pound sledge, trying to drive this specially cut piece of steel that Bill got made one day while he was back in the lab. He came along with this thing, and that transformed this job. It just couldn't get it going otherwise. So yeah, it was tricky. Oh, it's only a £7 hammer, sorry. Yeah. And we needed this underneath as well because we had to mount the handrails. The handrail installation, well, because the deck changes angle all the way over, we had to have some means of fixing these handrails that are there in the right place. So there was just enough. We had to position these handrails just right so that there was enough sticking down to put a plate up underneath. We had to drill through the box beam to get it held in place with a glass fibre dowel. And then this plate came on underneath. That's the pin getting driven into the box. And then there's the other plate being stuck underneath. And yeah, it was, you can see the weather's closing in at this stage as well. When you can't see the hills up here, you know it's not good. But at least working under the deck, you could do something. So here's a specially made device for driving the top cover plate down because they were a very tight fit on the thing. There was a nicely machined plate went onto the top of the handrails to seal off that box. And the handrail was put together with, there was this sort of like aeroplane wing section on the top, which was drilled for these tubes to go into, same at the bottom. And the tubes were drilled about 10, 15 mil from each end. And we had to thread a fiberglass rod right through the length of these panels, through each one of those tubes in the balustrade, and then anchor them off somehow. In the top of the end here, there was a slot through these handrails that a glass fiber plate went into, and you pull the handrail, the post over a bit, put the panel in, and then put the next one on at the start. The golf club were very good, the members, because they found they had a job that they could help us with. So the clubhouse was strewn with tubes and plates and box sections for that. Very useful. So that's the handrail installation. And that's what happens at the end of the day. Absolutely zonked. That is me, by the way, with the beard. Didn't have time to shave in those days. So that's my bit.
We've probably got a few minutes to go through the last bit as well. It was quite big news at the time. The won some awards and got some press. I think probably the most delightful thing that came out of it is this some unnamed poet did a version of McGonagall's poem published in The Economist. I won't try and read it in an appropriate accent. The obvious question then is how's it performed in the meantime? If you look at it from the south, it looks fine from a distance. If you turn round to the other side, there's more striking discoloration, but there's basically a lot of lichen and moss growing. There's no particular indication that I know of that that's causing a problem. It's interesting that it doesn't look pretty. Lichen and moss on a stone bridge looks just fine. On a beige plastic bridge, it doesn't look quite so in place. More problematic is the bits of damage. There's two things going on there. One is a huge growth of moss in the gutter at the edge, and the other is the fraying of the handrail. But the whole handrail system is the big problem, I think. Just not fit for purpose. The design didn't work. You can see all the generations of attempts to fit that back together. One of the problems was that the little dowels have a grain to them, and the rails rattle and the dowels ratchet. And within months, those dowels have started ratcheting and falling right out. The end where the material is exposed at the end, it suffers a bit as well. There have been a couple of fairly in-depth looks at this from Tim Stratford at Edinburgh. I guess he might be doing another one in a couple of years for 30 years. I think he's done one at 10 and 20. One of the things that happened fairly early on was that some idiot drove a tractor and a trailer full of sand across the bridge and cracked the top surface of the deck. So that triggered a revisit, and they put on some additional GRP plates and some strengthening around the cross beams. Impact is a problem. It's brittle if you hit it from the side. So this has been caught by a vehicle again, I believe. Cross bridge at your own risk. Obviously, there's a liability concern, and in particularly the handrails have caused a lot of worry. I think it would be a fair argument to have about whether the risk of crossing this bridge was greater or lesser than squeezing between the vehicles on Wade's Bridge. I'd go for this one myself. I think maintenance questions, that some of these things, like for example this metal grille, which presumably is there to try and inhibit taller vehicles. It was. Oh, it was a closure. Yeah. It was a closure. Along with that. Cut it open. Because the people who live on the north side of the river had become very used to having a nice, safe, quiet bridge to cross, and weren't at all happy about losing that possibility. But various things, including, I suspect, this have been attached using wood screws into the material. So that's not necessarily ideal as well. And just as a closing slide, that's obviously the tower of the new bridge coming in over the old bridge, and anyone involved in assessment of masonry bridges will be familiar with issues of liftoff in vehicles. That's a good example of what causes liftoff. If you imagine the 2 or 3 axles at the back of the lorry there, as it goes over the hump of that bridge with a long length of tower on it, you don't have many axles left on the ground. And that's what we have prepared, and that is 45 minutes.
Thank you. That was brilliant. It must have been something that was
so many slides
involved in as a student. You would take ownership of the bridge.
It's sorry, the club who owns the bridge. The golf club. But it's perhaps also worth saying that the golf club own it, but they have long since retreated from their 18 holes back onto the south side of the river, so their interest has gone. And so the question of who will maintain it and why is very much an ongoing problem.
Do you have any questions?
I have lots of questions, but a quick one to start with. Did any people fall in the river?
Some people jumped in the river.
I was the first one.
What?
I was the first one to jump into the river.
Fraser, going to come round so that they.
No, but that was on purpose, you mean?
Oh, yes, yeah.
Yeah.
No, they put a safety line right along the centre of the
Right,
deck
uh-huh.
when it was put up.
Recently, I've been concerned with two problems. One is handrails, or a very particular handrail, and another is the condition of GRP after 50, 60 years. I mean, why all the growth on the surface? I mean, have you?
It's clean air.
Hmm?
Clean air.
And that,
It just-
lichen will grow.
It's just what happens to every surface in Aberfeldy. It's that there isn't a lot there.
and presumably it's you can't clean it off really, or it'd be a lot of work to.
And if you could get up there, you could clean it, yeah. But who's
You couldn't use chemicals because they'd go in the river, wouldn't they?
Yeah, I would imagine that the Environment Agency equivalent SEPA would have some
No, it wouldn't.
concerns.
The handrail, I mean, is it by law, should the handrail not work or whatever horizontal loading you choose? I mean, it's effective now. Does that matter in regulation terms?
It's a thorny problem that can only be sorted out by quite significant expenditure.
Mm-hmm.
And the golf club do not have the funds to do it.
And final question, and all the sections have lots of voids in it.
Yes.
Does water get in there? Is there any chance of water piling up in there and doubling the width, tripling, whatever it is? Start.
I don't think so. There is no bonding between the ends of the deck plank, so there's always, the water's running down the hill. It can.
So if water got in, it can get out again.
Yeah, it gets out.
Yeah, this is something that Bill was at great pains to teach me in when we were dealing with instrumentation. And my naive approach was always to try and keep water out. Bill was always keen to point out that if the harder you try to keep water out, the better you will keep water in.
Okay. Let somebody else have a go.
Any more questions?
Yes, I'd like to ask why it didn't have a lot of followers in the immediate aftermath. It seems like the idea was proven. It seemed like it was a good one, low maintenance, all that kind of thing. It could even be built by students. So shouldn't it have been followed up by a whole heap of other similar bridges in the following years?
I have a vague recollections that one box type beam was built, a beam bridge was built somewhere in Himalayas or something like that. Just as an example.
There have been others.
Yeah.
No, I mean, none quite as all composite, but of course that was pushed to the limit because of the nature of the project. Yeah, there's an obvious question of whether pushing it to the point of doing the entire handrail in composite created the problem, some of the problem there.
It's bloody horrible on your hands,
I think
because the plastics like slowly
the
degrading.
surface plastic, right?
Yeah.
I suspect that there are. So the very thing that made it a fascinating and exciting project to be involved with all of that problem solving is perhaps relevant. The industry knows how to build in steel and in concrete. And contractors who are used to who like to build things, they like to get on and build things. They don't want to be messing around with new materials and trying to work out how to do it. May contribute. There's obviously some movement now. There's network rails, blow footbridge might change the scene quite considerably if they build it at the scale that they have in mind. It's not going to be 63 meter span, but Perhaps that's sensible.
Yeah.
But you didn't show any design drawings or assembly drawings. Some of the details I found a bit difficult to understand. One thing I couldn't quite understand was your choice of erection sequence. That you put the cables up first, obviously, and then the hangers with the hangers attached, and then you chose to attach the cross beams rather than launch the edge beams from the edge and to take them out. Connect. I suppose well, why didn't you launch the edge beams separately from the deck? I suppose is the question, because then you could have dropped them down onto the cross beams.
I think with that cross section that we had, there is no way you could have put the deck out to go between cross beams, because you would have had to possibly build every single panel separately, as opposed to launching out the whole deck. Yeah, there were things that could have been done differently.
Always are.
And did you?
Come on, I'll ask you. You're supposed to ask a question.
Sorry, can I just ask one more?
Yeah.
To what extent did you allow for the fact that things would need replacement? And it looks to me as if your handrail detail didn't, it assumed it would have the same life as the rest of the bridge, which may or may not be correct.
It's not correct. That is the weak link, definitely the weak link.
Right.
It's what the bridge is what Maunsell designed.
Right.
And that's the system they were promoting. It just happened that we got involved in building their first one and trying to solve problems, and it's trying to do it in all composite was, I think, an error.
Yeah, I guess on that point that at least the handrail is the most replaceable part of the whole system. Should someone find the funds to do so? Obviously, the attempt was made to close the bridge to solve the problem, but the attempt failed.
Yes.
Yes.
Okay, thanks.
After you.
After it was built, how much did it vibrate or deflect? And you say you filled the sections to provide mass.
Yeah.
Did it vibrate very much?
When we had the opening ceremony, the piper went across first, and then the VC of the university and the golf club president, and then the student who built it, and then others. As the students got on towards the middle of the deck, they had it moving sideways, probably about this much.
Oh.
Yeah. Because when you were going, and once, like with the wobbly bridge here, you couldn't not keep in that step. You couldn't do anything other than steps like that.
And another question: were Maunsells involved on site?
They had an engineer on site right through it. Yes, Jenny.
And occasional visits from Peter, who may be on.
Well, Peter was in cool photos.
I think that is. So the dynamic response has been measured, and it's been measured again since. So there is some evidence of slight progressive change in the dynamics, but it is slight and it's not completely univocal.
Yeah.
I'm directed to ask, if you were to do it again, what would you do differently?
What would I do? We should have built the whole length of the deck on the golf course level. We could have had our tent, built a panel, you push it out,
space
built
to
a panel, you push it out, and then pull the whole lot over in one go. Would have been far, far better. To try and stitch these two ends downhill from the deck was just disaster.
Oh, I see. It wasn't launched just from one end.
Yeah, it was launched from one end to get the centre span down. And then the two side spans were completed away from there.
Ah, right. Right.
Which again was difficult because you had to have two gangs
Yes.
working. Yeah. But it was too late by the time we pulled the deck across to realise that we were going to have these big problems with the rain.
Just a question about the design. I was sort of slightly surprised when I looked at the bridge to see the sort of splice parts under the cross beams, and I thought, why on earth don't the main beams just ride over the cross beams, which would look natural, whereas the extra bits spliced on, I thought looked a bit ugly by comparison. Do you consider just having them simply resting on top of the cross beams and maybe clamped somehow too?
Bill did a lot of this, and I was just the guy who'd been working on site that was a useful person to have on site and problem solve. But we couldn't change it once we started. But
once you offer it up,
yeah, it's only when we started trying to get these things into place that we realised that we were going to have to bend everything to try and get it in place.
Well, I just wonder if it was necessary to notch the beams in order to get the curvature, or if you may.
No, it would have been
enough
was
just to
extremely
flex.
It was very flexible. Certainly, as the launching nose was going out, the bit that was sticking out to make it ride up onto the next crossbeam was really, really useful. If we'd had a different method of filling the boxes that maintained the gap, then that might have been better. But yeah, we couldn't tell how flexible the whole thing was until we started pulling it. That it was, oh look, it's going up over there, and it's got a big kink in it where the box is. And we had to have enough space in it to make sure that we could actually get it down over the box, the crossbeam. Yeah.
And how much glue was involved in the bridge? Was glue regarded as part of the design, or was glue regarded as a bit of a solution to the other problem here or there?
No, glue was used right through, but when we were putting the boxes together or the deck together, there were two stripes of glue down along the surface, each side of the dog bone, and to some extent, some of that glue, trying to pull the things together, was you had so much glue in there that it didn't want to move out of the way, and some that did move went into the dog bone, and then got even harder to dry.
And
Yes,
even harder to dismantle, I mentioned.
Yes. Yeah.
might have it.
I'll go for the online question and then I'll come straight to you. So we have one online question as how do you monitor the dynamic response of the bridge, whether that's something you can involved with or not?
There was a team came up that were doing the monitoring of the Aberfeldy Bridge here that came up to compare what we were doing up there. Because at that time it was only just finished, nice, pristine, clean, and everything. Yeah.
Back to the glue, manufacturers tend to have some quite onerous instructions how to use it. Did you have any problems?
There were some problems. We had were they electrical air operated?
I was trying to remember that.
I'm trying to remember whether they had air operated or electrical things, but actually after a day of trying to fix things together, but just squeezing in a glue gun was just murder. My hands were absolutely shot. I used to lie in bed in the morning at times and do this to try and get life back into my arm.
So the manufacturers didn't require any primer or anything like that, or
We
or setting times?
It was white. It was IPA to clean it. So
Okay.
yeah.
Thanks.
Hi. Can I comment on usability in service? Somewhere in the early noughties, I was on holiday in Scotland and decided I would like to come and have a look at the bridge with the permission of the golf club. At that point, I was a single parent, so my daughter, primary school age, was along with me. Yes, I had an interesting time looking around at the details. She kept herself amused during the time that I was doing this. By the end of that day, the palms of her hands and her fingers were really red and inflamed. It seemed to be the classic issue of contact with glass fibre.
Yes. Could she reach the handrails?
I don't know exactly what she was looking at, whether she was on the deck of it, running her hand along the handrails, or whether she was down on the ground on the side spans.
Yeah, the handrails were eagle. I don't know that many of the other things were. Certainly the box sections were, when they were filing them, were a bit of a pain, but with my adaptation things, that got eliminated.
Obviously, a few areas where there was impact damage, the fibre might have been exposed. But I would have thought that the handrails were the obvious, so were the figure of suspicion of the point, I guess.
How long ago did you
Which is
say?
ideal, of course, because that's the bit that you held.
How long ago you were there?
I don't have a clear memory of this. It was after 2000, and probably within the next 5 years after that.
So 92 to
10 years.
10 years.
Yes.
Yeah, it could well have been on the uprights of the handrails as well. She'd been sort of, looking out through them.
I mean, she remembers the discomfort of it. I'm not sure I could ask her exactly what was it you were doing.
No, it was just horrible. Yeah. Rubber gloves.
Yes. Box of gloves at each end.
Yeah, that'd be a big box of gloves at each end.
We've got Peter Head on the call, but we can't work out how to talk to him at the moment.
Can I try talking?
There we go, brilliant.
Hi, everybody. It's a great pleasure to be here. And thank you very much for your presentation. I've got a few things to contribute. One is that in the rush to get the materials for the bridge. Sorry, can you hear me?
Yes.
Oh, right. In the rush to get all the materials for the bridge in place, the suppliers could not supply the handrail materials using the specified resin. The sections that they had available used an orthophthalic polyester resin rather than isophthalic resin, which is the one that's UV resistant. So there was a huge compromise in the handrails, which were not the specified resin, and therefore that's the reason they've deteriorated, because it's an orthophthalic resin. And unfortunately, there was no other option.
Right, we have an answer about the handrails, that the getting all these bits and pieces in time, that we got supplied with something that was not UV stabilized for the handrails, hence it degrades and you get glass fibers in your hand. Simple.
Yes. I was wondering about the imposed load that the bridge was designed for. Was there an area per square meter or was it a total load? And also whether the bridge has actually been load tested after completion and how that went and whether the deflections met the models basically.
I didn't catch all of them, but I heard something about load testing, and yes, it was. Just that the golf buggy with the sand on the back was too concentrated.
It has been proof loaded.
Proof loaded, yes.
Has it been proof loaded locally or all over the length of the bridge?
I can't remember, but some of these things, because term started before we finished it, and some of us had to go back to work.
Perhaps the number of people who actually crossed the bridge at the third day might have been the load test, I guess.
Yeah.
Could I make another point? Could I make another point about the bridge design? Is the bridge design the bridge design is not load critical, it's only deflection critical. So it has a massive factor of safety in terms of load carrying capacity, and you'd never be able to overload it. It's all about deflection and stiffness.
It won't work, so Hamish, you can relay that.
Another input from Peter, that the bridge is deflection, not load critical. There's no way you could overload it. I think the problem with the vehicle that went over was local damage to the top surface of the head, rather than to the bridge itself. And I had a question that I was going to pose back to Peter, but having run back to the microphone, I've now forgotten what it was, but it might come back.
Yes.
Oh, yes. A question really about the legalities, please. Was the design life specified at the outset? And is anybody taking the sort of overall interest in it, or is it on private land? I was just wondering about the sort of medium and short term use of it and safety wise.
I wish I knew. It's the answer, really. It's on land that is owned by the golf club at both sides, but as I say, the funds are extremely limited. So
I think that's the long and short of it, isn't it? That they have tried to take it out of use because they can't afford to maintain it. The problem is that the residents of the area have other ideas. So there's an ongoing sort of issue there.
That pirate tractor did it.
Peter might be able to tell us what the design life was. I don't know off the top of my head.
Yeah, if you can hear me, Hamish. The design life was extremely long. If we'd used the right resin for the handrails, the materials would have gone on for forever, effectively. There's no deterioration mechanism that would shorten the design life, either for the cables or the deck. So the design life is very, very long. We don't really know, of course, because these are materials that haven't been used in service for more than 10
More than this.
20 years. But in theory, they will last pretty much forever.
Yeah, so more or less open-ended design life, notwithstanding the issue with the handrail, which has UV damage. Thank you, Peter.
Obvious. Do we have any more questions?
What?
The problem with what loading to adopt for a footbridge is not that simple. Because of course, almost all the time, there's no load in it at all. Then just occasionally it carries really quite a significant load, and the opening ceremony is the obvious one.
Yeah.
And most bridges, after that, the initial wave of enthusiasm, get very little load. But was it the Coronation Bridge in Glasgow that we went to see many years ago? That was severely damaged on its opening day, just because of the sheer pressure of people who turned up, the number of people who turned up. And it survived. I can't remember if it's still there now, but anyway, it survived for quite a while. And then a few years ago, or quite a few years ago, there was a celebrated case in Belgium where a cast iron wrought iron footbridge crossed the lake to provide a shortcut for people. And it became known as the venue for wedding photographs. And of course, you get a whole load of people gathered together for a wedding photograph, and you can easily build up 3 or 4 kilonewtons per square meter. The normal loading is, I think, for rural footbridges, that most local authorities adopt is either 2.5 or 3 kilonewtons per square meter, which is okay for pedestrian loading. But then you get the local horse riders going across, and the point load from a heavy horse can be quite significant. So there's more loads you need to consider in the design than you might imagine, so you try and use solutions which are robust against a number of possible loadings. Anyway, not that simple. Thanks.
The question of what will people actually do is important.
Sorry?
The question of what will people actually do?
Yes. Yes, unfortunately, they're not the design criteria. No, I really, Bill took you to see it, but there's a lovely little bridge just east of Dundee, the Linksleader Bridge.
Oh, yeah.
Yeah, a beautiful little
Cast iron.
The cast iron wrought iron. Yeah. 1820s blacksmith made. And that was in a terrible state. And Dundee city engineers did a wonderful job in designing its restoration and getting it done. But when I went to visit it, or I visited a few times, there was nobody about. Then they built the housing estate just to the south of the bridge and carried on to the north of the bridge. All of a sudden it became very busy. And you can just imagine that wedding party scenario evolving there, because it's a lovely little thing, absolutely smashing little bridge. So it's only about 40-foot span, but it's a good piece of work.
Yes.
Okay. Well, thank you very much again for a fabulous talk.